Day, everyone. So today we are from Group 2. We are going to present about the experiment for minor losses in pipe. Okay, good day, everyone. Today from Group 2, will present about the experiment for minor losses in pipe. Our group consists of 4 members, which is Darshana, Divya, EILEEN, and myself, Jasmine. Next. So I will talk about the report summary. So this experiment is carried out to determine the loss coefficient and minor head loss in pipe components or fittings for different water flow rates, pipe diameters, and pipe bends. Energy losses in pipes used for the transportation of fluids are essentially due to friction, as well as to the diverse singularities encountered. These losses are usually converted into head reductions in the direction of flow. The knowledge of data of such transformation allows the determination of the necessary power needed for the transportation of the fluid between 2 points. The review of the different relationships allowing the determination of these losses and the comparison to the experimental results obtained. Next, I will pass to the next member to present.
As for the theory, the flow in the piping system at different flow rates may be required to pass through a variety of fittings, bands, or abrupt changes in area. Additionally, head losses called as minor head losses (HLM) are encountered primarily as a result of flow separation. By simplifying the Bernoulli equation between 2 points for the horizontal pipe, the pressure loss and total head loss could be determined as follows. The equation 1 shows the equation 1 is used to find the HTL, which is the total head loss. After modifying the first equation, we get the second equation and the third equation is used as well to find the second equation. Um, Next, the value of KL is strongly dependent on the geometry of component considered as well as the fluid properties, includes the Reynolds number, and the mathematical function of them can be expressed as the equation 6. In many practical applications, the Reynolds number is large enough so that the flow through the component is dominated by inertial effect, leaving the viscous effect as secondary importance. In a flow which is dominated by inertial effect, it is usually found that pressure drops and head losses correlated directly with the dynamic pressure. Therefore, the friction factor for a very large Reynolds number is fully developed pipe flow is independent of the Reynolds number. The same condition is found to be true for flow through pipe components or fittings. Thus, in most practical cases, the KL for components are a function of geometry only. In this experiment, the KL value and HLM, which is the major head loss, a minor head loss in pipes for different water flow rates, pipe diameters, and pipe bends will be determined. The description related to each of the tested geometrical is as follows. First, sudden expansion or enlargement and sudden contraction (KL) for sudden expansion or enlargement and contraction in circular ducts or pipes are shown in figure 2. Note that the losses for a sudden expansion enlargement are based on speed of flowing medium at region 1. For the sudden contraction are based on the speed of the following medium at division 2. This is the figure showing the loss coefficients for flow through sudden area changes. Next, the value for KL for the fluid flows through a sudden expansion, enlargement, and contraction can be obtained by considering the continuity equation, momentum equation, and the energy equation between point 1 and 2. And this is the figure 3, where shows the typical values of KL for pipe components and fittings. I'll pass to the next presenter.
So I'll be going through the methodology for this experiment. First, we need to determine the direction of water inflow and outflow for the tested pipe section. Second, we need to fully open the inlet valve of tested pipe section and close the inlet valve for a non-tested pipe section. Third, turn on the pump and slowly open the outlet valves until maximum and wait for a while in order to remove any air bubbles for the tested pipe section. Fourth, identify the inlet flowing pressure and the outlet flowing pressure for the tested pipe section and connect the manometer tubes for those H1 and H2 of the tested pipe section to the 2-tube manometer. Fifth, record the values of H1 and H2 at the 2-tube manometer. Next, determine the actual water flow rate by recording the time taken to collect the 3 liters volume of water at the tank. Reduce the opening of outlet valve and repeat steps 4 till 5 for 5 times for different values of actual flow rate. After completing this, remove the manometer tubes first to avoid the bubbles in the tube. Next, with pump in running condition, repeat steps 1 to 7 for the other tested pipe section. Lastly, once the experiment is completed, remove all the manometer tubes from the system. Fully close the inlet and outlet valves and turn off the pump and the main switch. Next, I'll pass to raw data analysis.
So this is the table and the data needed for the sudden enlargement and sudden contraction. In this table, we need to measure the actual flow rate, the time taken, H1, H2, and also difference in height, difference in H. Next. The second table, we have the table of data for the two types of branches, which is Y type and T type. For this two types of branches, also we need to get the data of time taken, actual flow rate H1, H2, and difference in H. Next. And lastly, this is a table of data for different types of elbows and pipe bends. In this table, we know that we have two elbows with the angle of 90 degree, two pipe bends with the angle of 90 degree, and also two elbows of with the angle of 45 degree. Here also, the data that we need to find also the same with the other two tables, which is the time taken, Q actual, H1, and H2. Next, I will pass to EILEEN for the results and discussion.
Next is the result and discussions. So for the table 1 is the table of the result for data of sudden enlargement and sudden contractions. Next. So this one is the table of the result for the data of Y type and T type. And next one is the table for the result of calculating the 90-degree angle, 90-degree bend, and 45-degree angle. Next. So for calculate the minor heat loss and loss coefficients and calculate the friction coefficients. So for the sudden enlargement, the first one outer diameter is 0.02 meter and T1 is 0.0015 meter. For second outer diameter is 0.032 meter and T2 is equal to 0.0018 meter. So for the first one, inner diameter is equal to first one outer diameter minus 2 T1. So we can get the 0.017 meter. So for the second inner diameter, we can get the 0.0284 meter. So by getting these two diameter, we can calculate the area 1 and area 2. So we also can calculate the velocity 1 equal to Q divided with A1, and then V2 equal to Q divided with the A2. So for Reynolds equal to velocity, the first one velocity times the first one inner diameter divided with the kinematic viscosity, which is at temperature T equal to 36 degrees Celsius from the table by using the interpolations. So for the friction coefficients, we use the formula of Brussels, and the KR is equal to 1 minus area 1 divided with the area 2 square. So for the HL, for the minor heat loss equal to V1 minus V2 square over 2G. So for all the calculations, we can get the average minor heat loss equal to 0.1467 meter. And for the loss coefficients is equal to 0.4117. And for average friction coefficient is equal to 0.0222. Next. Same with the sudden enlargement. For the sudden contractions, the first one outer diameter is 0.032 meter. The second outer diameter is 0.02 meter. So using the same calculations method with the sudden contractions, we can get the average minor heat loss is equal to 0.0716 meter, and the loss coefficient is 0.4117, and the average friction coefficient is 0.0262. Next. So for the Y type, the outer diameter is equal to 0.02 meter, and the inner diameter is equal to 0.017 meter. So from the table of the loss coefficients, we can get the KR for Y type is equal to 2. So the minor heat loss, the equations of minor heat loss for the Y type is equal to KR times V2 divided with the 2G. So we can get the average minor heat loss equal to 0.2665 meter. The loss coefficient is 2. The average coefficient of friction is equal to 0.0253. Next. So same with the Y type, using the same calculations method. So for the T type, we can get the average minor heat loss is equal to 0.3451 meter. The loss coefficient is equal to 2, and the average coefficient of friction is equal to 0.026236. Yes. So for the 90-degree angle, the K1 for 190-degree angle is 1.5. So if got 2, we need times 2. So we can get the KL for 2 times 90-degree angle is equal to 3. So using the same method as before, we can get the average minor heat loss equal to 0.4579 meter. The loss coefficient is totally equal to 3. and the average coefficient of friction is equal to 0.0237. Next. So for the 90-degree bend, so KL for 190-degree bend is equal to 0.7. So for 2 times 2 equal to 1.4. So the average minor heat loss is equal to 0.1925 meter. So the loss coefficient is totally 1.4, and the average coefficient of friction is equal to 0.0257. So next, for the last one is 45-degree angle. So for the KR for 145-degree angle is equal to 0.04. So for 2, we can get the 0.8. So overall, we can get the average minor heat loss equal to 0.1221 meter, and the loss coefficient is 0.8, and the average coefficient of friction is equal to 0.0237. Next. So discuss the effect of different water flow rates, pipe diameters, and pipe bends on the value of loss coefficients. So the first one is the effect of water flow rate on the value of KL. The KL has no dimension since it represents a proportionality constant between the energy loss and the velocity head. So the magnitude of the KL is determined by the structure of the system, causing the head losses and velocity of flow. So if the water flow rate is high, the friction loss in pipe is greater. Hence, the loss coefficient is also greater. So second is the effect of pipe diameters on the KL. The smaller the pipe diameter, the more friction it will contain and more energy will lost. Hence, the higher the loss coefficients. So the third is the effect of pipe bends on the value of KL. The longer the pipe bending, the smaller the loss coefficients. Next. So the factor contributing to error or inaccuracy in experiment data. The first one is the parallel error. Parallel error will occur when the eyes are not perpendicular to the measurement scales. So the human error such as the mistaken data can also lead to the calculations error. The presence of air bubbles trapped inside the connecting tube which connect the pipe to the manometer also will affect the flow of water and lead to mistake. So the last one is the environmental factor, such as the vibrations, temperature changes, and electronic noise may influence the accuracy of the measurements. So the possible recommendations to improve the existing result is, the first one, we need to measure that our eyes is perpendicular to the measurement scale during taking the data to avoid the parallel error. Second, we also need to measure that we take the correct data and repeat the calculating to get the correct answer. Third, we need to remove all trapped air bubbles by opening the valve to allow the overflow of water before the experiment. Last one, we need to measure that the environment that we do experiment is in safe and quiet conditions. That's all from result and discussion. I will pass to the next for conclusions. Thanks.
Okay, so I will be going through the conclusion. The conclusion for experiment 4 is number 1, if the water flow rate is high, the friction loss in pipe is greater and the loss of coefficient is also greater. Number 2, the smaller the pipe diameter, the more friction it will contain and more energy will be lost. Hence, the higher the loss coefficient. And lastly, the longer the pipe bending, the smaller the loss of coefficient. So the references for this experiment is as shown. That is all from our group 2. Thank you.